Development of a theory. Before you read, what do you think? Read the three statements below and decide whether you agree or disagree with them. Place an A in the before column if you agree with the statement or a D if you disagree. After you have read this lesson, reread the statements to see if you have changed your mind. Key concept. What evidence supports the theory of plate tectonics? Lesson 2. Read to learn. What can scientists see at the bottom of the sea? Scientists began exploring the seafloor in greater detail during the late 1940s. They used a device called an echo sounder to measure the depths of the ocean floor. An echo sounder produces sound waves that travel from a ship to the seafloor. The waves echo or bounce off the seafloor and back to the ship. The echo sounder records the time it takes to echo to return. When the ocean is deeper, the time it takes for the sound waves to bounce back is longer. Scientists calculated ocean depths and used these data to create topographic maps of the seafloor. Ocean floor topography. These new topographic maps showed large mountain ranges that stretched for many miles along the seafloor. The mountain ranges in the middle of the oceans are called mid-ocean ridges. Mid-ocean ridges are much longer than any mountain range on land. The maps also revealed that underwater mountain chains had counterparts called ocean trenches. Ocean trenches are deep underwater troughs on the seafloor. The Mariana Trench in the Pacific Ocean is the deepest landform on Earth. It is so deep it could fit Mount Everest with 6 Empire State Buildings stacked on top. What pattern can be found on the seafloor? Using rock samples from the ocean floor, scientists were able to determine the age of the ocean floor and create isochron maps. An isochron is an imaginary line on a map that shows points that have the same age, that is, they formed at the same time. These isochron maps of the ocean floor revealed an interesting pattern. The ages form a series of stripes across the seafloor parallel to the mid-ocean ridges. Each stripe represents the age of that strip of crust and match from one side of a ridge to the other. Relatively young ocean floor crust is near mid-ocean ridges. Older ocean crust is found along ocean trenches. The seafloor ages as you move further away from a mid-ocean ridge on either side of the ridge. So how do continents drift? Why would the seafloor age as you move further away from mid-ocean ridges? In the 1960s, scientists proposed a new process that helped explain ocean floor features, ages, and continental drift. This process is called seafloor spreading. Seafloor spreading is the process by which new oceanic crust continuously forms along mid-ocean ridges and is destroyed at ocean trenches. The conveyor belt. When the seafloor spreads, the rock below the seafloor becomes molten. Molten rock below the Earth's surface is called magma. The magma is less dense than the surrounding mantle. The magma rises through the cracks in the crust along the mid-ocean ridge. When magma reaches the Earth's surface, it is called lava. As lava cools and crystallizes on the seafloor, it forms new oceanic crust. Two halves of the oceanic crust spread apart slowly and move apart like a conveyor belt. As the seafloor continues to spread apart, new crust that is forming pushes the older crust away from the mid-ocean ridge and eventually sinks at ocean trenches. This explains why the closer the crust is to a mid-ocean ridge, the younger the oceanic crust is. Scientists concluded that as the seafloor spreads, the continents must move along with it. Seafloor spreading is the mechanism that explains Wegener's hypothesis of continental drift. Continents do not move through the solid mantle or the seafloor. Instead, continents move as the seafloor spreads along a mid-ocean ridge. What is the theory of plate tectonics? By the late 1960s, the concept of continental drift and seafloor spreading led to a more complete theory called plate tectonics. The theory of plate tectonics states that the Earth's surface is made of rigid slabs of rock or plates that move with respect to each other or in relation to each other. This new theory suggested that the Earth's surface is divided into large pieces of rock. These pieces are called plates. Each plate moves slowly over Earth's hot and semi-plastic mantle. Tectonic plates, Earth's outermost layers, are cold and rigid compared to the layers within Earth's interior. The cold and rigid outermost rock layer is called the lithosphere. The crust and the solid uppermost mantle form the lithosphere. The lithosphere varies in thickness. It is thin below mid-ocean ridges. It is thick below continents. Earth's tectonic plates are large pieces of lithosphere. These plates fit together like the pieces of a giant jigsaw puzzle. Directly below the lithosphere is a very hot part of the mantle. This layer of Earth is called the asthenosphere. Even though it is solid, the asthenosphere behaves like a plastic material because it is so hot. The asthenosphere flows below Earth's plates and enables the plates to move. Look at the map below. It shows Earth's major plates and their boundaries. Notice how some boundaries in the middle of the oceans. Many of these boundaries are located at mid-ocean ridges. The Pacific Plate is the largest plate. The Juan Fuca is one of the smallest plates. Over billions of years, continents have moved great distances, collided, and spread apart. Tectonic plates move slowly, only 1 to 9 centimeters per year. But these massive plates have so much force, they can build tall mountains, form deep valleys, and rip Earth's surface apart. Because tectonic plates move very slowly, most changes to the Earth's surface take a long time. But some changes, like earthquakes and volcanic eruptions, occur very quickly and violently. You will learn about these changes in the following lesson. After you reread the statements at the beginning of the lesson. Fill in the after column with an A if you agree with the statement, or if D, you disagree. Did you change your mind?